So you can imagine with this, what is the picture that is coming in your mind after seeing this photographs? What do you say? Let's suppose here is who is here. Let's suppose any person that is A is here. Is he in any equilibrium condition, or he is in condition of jumping from this wire? What do you say? Will he survive if he will jump from this wire? No. Raghav, how many times I have to say you that please turn on your camera? While joining the live class, you will have to always turn on your camera. It is only with the case with Anil that he is having some problem, like he is suffering from diseases. That's why I have allowed him. Else, everybody will have to turn on their camera. I don't want to repeat the same thing again and again in class. Yes. So guys, so what will happen? See, you might be going with your mom or dad to market, right? Equilibrium, if I will take example from the daily life, you might be going with your dad or mom to bring some vegetables sometimes some grocery items from the market. So the shopkeepers used to do what? They are just weighing the vegetables with the that is with weighing machine, right? So sometimes what we are doing, what we are checking, that whether the left hand side and right hand side, whether they are equal or not, yes or no. If they will be unequal, it means they have attained the equilibrium condition, right? So that is one example that I am taking from the daily life only, right? But in chemistry, although the meaning is same, but there will be various processes will be there. Is it okay? Is it okay, guys? Now, see here. So I have tried my level best to show you that how we can attain equilibrium with this diagram, right? And later part we will be seeing more things, right? Now, this is for the recall part. I hope everybody is familiar with the term entropy. Yes. So we can measure the disorderness from the entropy. Disorderness. Atacha, I hope you will know because you have explained this topic. Entropy is what? Disorderness. Can we say disorderness? The maximum entropy will be finding where? Maximum disorderness will be found where? Solid, liquid, or gas. Where we will be finding the maximum disorderness. So guys, so the order will be what? This will be the order. Okay. Okay, fine. Now see here, actually chemical equilibrium. So we will be, I will be connecting with this topic. See here. This is here showing what? This is forward reaction, right? And this one is this is happening what here? See, one quantity will be increasing and second quantity will be decreasing. So forward and backward reaction will be taken place in case of equilibrium. Forward and backward. This arrow showing that what? Forward reaction is there. Forward and backward reaction, it is happening both the reaction at the same time, then we are calling that at any point of time they will attain the equilibrium condition, right? So forward and backward condition will be there in case of equilibrium, right? See here. So just for the part of introduction only, it is an experimental fact that the most of the processes, including chemical reactions, right, when carried out in a closed vessel, do not go to completion, right? We have seen so many reactions that in the closed vessels they do not go to completion, right? So they proceeds to some extent, leaving considerable amount of reactants and products, right? So some amount of reactant and some amount of product will be, that will be remain in that. Okay. So when such stage is reached in a reaction, it is said to be that reaction has attained the state of equilibrium. It means what? If what has happened after reaction, some amount of things are what remained with reactant part, and some amount with the the product part is remained left out. So we will be calling that they have attended the position of what? Equilibrium. That is what physical equilibrium we can say, right? Is it okay, guys? Equilibrium represents the state of a process in which the properties like temperature, pressure, concentration, etc. of the system do not show any change with the passage of time. Is it okay? If I am taking an example of physical equilibrium, what happens? What happens with physical equilibrium? See guys, you might have seen ice, okay, and water, right? This is what? Water. Suppose this is what? Water, and this is what? Ice. Do you know that ice at 0 degrees Celsius start melting, right? At 0 degrees Celsius, ice turns into what? Water. And at the same time, at 0 degrees Celsius, water turns into ice. Is it okay? Am I right here? Am I right here, guys? What do you say? So at the same time, 0 degrees Celsius, the ice will turn into water and water will turn into ice, right? So if the experiment is going in a closed vessel, so what you will be seeing there, nothing is changing. Neither the ice is converting into water or water is converting into ice. That will remain same. That is what they have attended the position of what? Equilibrium. Is it okay? So see here. So what is saying here? In all processes which attend equilibrium, two opposing processes are involved. Equilibrium is attained when rate of two opposing processes become equal. If the rate of two opposing processes become equal, then the equilibrium will be attained, right? So if the opposing process involve only physical change, the equilibrium is called physical equilibrium. If the opposing process involve only physical changes, the equilibrium is called physical equilibrium. Okay. If the opposing process are chemical reactions, the equilibrium is called chemical equilibrium. Is it okay, guys? So what is this physical and chemical equilibrium? If you want to write, please have a note of this. And after this, we will be starting with some examples as well. Okay, guys. Some common physical equilibria are solid into liquid, liquid into gas. So solid liquid, liquid gas, and gas solutions. We will be seeing the examples of all these guys, right? Now, how we are writing the equilibrium conditions, right? General chemical equilibrium represents as what? A, B plus B. Gives what? Let's suppose if I'm taking X plus Y. Please don't write this because we will be having so many examples in the later part of the PPT, right? Where A and B are what? Reactant, and X and Y are what? Product. And this A is what? Small a is what? The coefficient of A. Coefficient of B. The small b is what? Coefficient of B. Is it okay? Small x is what? Coefficient of X. Small y is what? Coefficient of Y. Is it okay? Any problem till here? Anyone, guys? Okay. Now, see here. The double arrow between the left hand part and the right hand part shows the change is taking place in both directions. That I have shown you here, that is what? The double arrow is what? The change is happening in the forward direction and in the backward direction. That is in both the direction. Is it okay? So whenever there will be equilibrium will be there, so you will be showing that you will be seeing that there is this reaction, this part will be always there. If it is this arrow is only there, it means what? Reactant is converting into product, but the product is not converting into reactant. But if it is showing, if the direction is like this, it means what? The reactant is converting into product, also converted into the reactant. Yes or no, guys? Is it okay? Let's suppose if I am saying that, let's suppose if I am taking that AA, right, and BB will be there, and the product that you are going to get is what? XX plus YY. Okay. And let's suppose if at any point of time, if I will increase the concentration of this B, if I will increase the concentration of this B, then what will happen? Can you imagine that what will happen? See guys, if you will increase the concentration of this B, so what will happen? The product will be increased, right? So that to make this in an equilibrium, the product will be increased. If you are increasing the reactant side, the product will be also increased at the same time, and to attain the equilibrium condition. Is it okay? Let's suppose if you are removing this part, then what will happen? Again what will happen? The see. So what will happen? If let's suppose if you are decreasing this part, or if you are removing this part, then what will be happening there? Either this will be increased or this will be decreased to obtain the equilibrium condition. Is it okay? Now see here. So the double arrow between the left and right hand side, right hand part, shows that changes is taking place in both the directions. First point is clear. Arrow will be showing what? The changes is happening in the left hand side and the right hand side. Now, second part is what? On the basis of extent of reaction, before equilibrium is attained, chemical reactions may be classified into three categories. What are these three categories? First is what? The reaction which proceeds in almost completion. The reactions may be able to complete their reactions. Second part is what? The reaction only up to little extent. Let's suppose the reaction started and it has not been completed. That is what? That is this point. And the third point is what? The reaction which proceeds to such an extent that the concentrations of the reactant and products are equilibrium are comparable. So their reactant and product are comparable. That much of the reactions has been happened there. Now, the different types of physical equilibrium are briefly described. See here. Solid liquid equilibrium that we have seen here. See. Solid liquid equilibrium that we are going to see here. What we are going to see here? Solid liquid equilibrium. See. The equilibrium existing between ice and water is an example of solid liquid equilibrium that I have given you earlier, guys. In a closed system at 0 degrees Celsius, ice and water attain equilibrium. Let's suppose we are having a closed system and at 0 degrees Celsius, ice and water, they will attain a position of equilibrium. Why? At 0 degrees Celsius, ice will turn into water and water will turn into ice. So both will be happening at the same time. So there will be no change that you will be going to see there, and the condition will be what? If you are seeing that there is no changes happening there, it means what? Their equilibrium has been attained there. Is it okay? So now you can see here, the equilibrium existing between the ice and water is an example of solid liquid equilibrium, right? In a closed system at 0 degrees Celsius, ice and water attain equilibrium. At this point, rate of melting of ice is equal to the rate of freezing of water. This equilibrium is represented that you can see here. So guys, what is this S description? If it has been written H2O, S, it means what? This is nothing, this is water. And water is in what condition? Water is in condition of solid. And solid condition of water is what? Ice. Guys, the formula will be remain same. We cannot change the formula. Now again, so there will be a two arrow will be there. One will be in forward direction and one will be in backward direction. And H2O, that will be in what? liquid, actually here there will not, T will be not there, actually L will be there. Okay guys, is it okay? So please have a note of these things. And everyone, done? Kaniska, done? Attachaya? Okay, fine. Now, liquid gas equilibrium, that we are going to see about what? Liquid gas equilibrium. Evaporation of water. See guys, let's suppose we are having a container in which what we are seeing that water. If you are heating this water, what will happen? The water will be changing from this water to water vapor. Yes or no guys? Right? And at the same time, if there is condensation is going on, see here, evaporation of water in a closed vessel is an example of liquid gas equilibrium, where rate of evaporation is equal to the rate of condensation. What is happening here? Actually here this is what? Liquid, right? So what will happen guys? Let's suppose water, you are heating this water, water is turning into what? Vapor. And again, this water is coming down, right? After vapor form, they will be coming down only, right? So at the same time, the rate of, see, at the same time, what is happening? Evaporation and condensation is happening there. Evaporation and condensation is happening there. So we will be calling this what? Liquid gas equilibrium has attended. So getting my point? So water, liquid will be turned into what? Water, gas, right? And at the same time, this gas is turning into what? Liquid. So we'll be calling this what? Liquid has attended or liquid gas equilibrium. Is it okay? Any problem till here? Now, solid solution. Just a minute, guys. See here. Actually, here gas solution is there, but somebody has written here solid solution. Gas solution will be there, right? See here. If you add more and more salt, let's suppose we are having a beaker and we are having some amount of water there. And if you are adding what? You are adding salt there, right? Or you are adding sugar there. Let's suppose you are adding sugar there. So after some time, what will happen? Like, let's suppose there will be a condition will be coming there. After that, you will not be able to add sugar into that. Why? Because there will be the solubility will be, the sugar can sugar can be dissolved after after like at certain amount of sugar can be added into the certain amount of water, right? After that, saturation solution will be there. That will be saturated. Like after that, you cannot put sugar into that. So what is saying here, if you add more and more salt in glass of water and stirred with glass rod, after dissolving some amount, you will find out no further salt is going into the solution. Getting my point? So either sugar or salt you are taking, after some time, you will be finding that that is not dissolving into the water. Why? The saturation has been attended. Saturation means what? Saturated solution you might have learned in your 10th standard. What is the saturated solution, guys? Anybody is knowing about the saturated solution? Saturated solution in what? See guys, at any point of time, like if you are having amount of water into a glass and you are doing what? You are adding sugar into that. After some time, what will happen? You are adding another spoon, 2 spoon, 3 spoon, 5 spoon, let's suppose 10 spoon, right? And you are stirring that. At some time or after some time, you will be finding that what? If you are adding amount of sugar into that water and you are stirring the water, you will find that the sugar is not dissolved into that. Why? Because the saturation solution has been obtained there. Is it okay? Any doubt? No? See, that we are going to see. The solution is now said to be saturated and in a state of equilibrium. At this stage, many molecules of salt from the undissolved salt go into the solution or dissolution, you can say, and same amount of dissolved salt are deposited back, that is precipitation. Guys, please try to understand here. What is this dissolution and what is this gas solution, or you can say that liquid solution. Now see here. So we have seen about what? Solid solutions. Then we are seeing what? Gas solution, right? Dissolution of gas in a liquid under pressure, right? Dissolution of gas in a liquid under pressure in closed vessels established what? A gas liquid equilibrium. See guys, you might be seeing that LPG cylinder that is coming to your home, right? What is happening there? Dissolution of gas in liquid. So you will be finding that after, like, let's suppose if you are having any chance to get the blank any time in your house, like any moment that you are getting that the blank cylinder is there. So you will be finding what? In the remaining part of that cylinder that is having like there is no gas is there, you will find that there is liquid is there. Why liquid you are finding there? Have you tried to ever know this, that why liquids are there? Why not solids are there? See guys, actually after compression, what has happened? The gas turns into what? Liquid. So dissolution of gas in liquid under pressure in closed vessel established a gas liquid equilibrium, right? The best example of this type of equilibrium is cool drinks that you might be seeing in your what? Coca-Cola. Coca-Cola gas, see, Coca-Cola liquid is there and CO2 gas is in there in this Coca-Cola bottle. Yes or no? You might be seeing just opening the cap of the cool drinks, you will be finding that what is happening there, the gas is coming out from the bottle. And what gas is coming out from the bottle? That is CO2 gas is there. Why they are coming? Because earlier it was compressed. That is, their pressure has been increased in the bottle, and now when it is coming into the contact of atmospheric pressure, so atmospheric pressure is lesser, right, in comparison to the pressure that has been given into the bottle. So that will be coming out. So liquid or gas is having what tendency? They are having the tendency that they will be moving from higher concentration to the lower concentration, right? Or higher pressure to lower pressure. They will be moving out where? Higher pressure to lower pressure, you can say, right? Let's suppose you are having what? A bucket is there, and let's suppose another bucket is there. And this bucket is full of what? Water is there, right? And if there is hole will be there. So the water will be coming out from this bucket to this bucket or not? If there will be any hole will be there in this bucket as well. So higher pressure level to lower pressure level, right? Or higher concentration to lower concentration. So we have seen that what? Gas solutions in equilibrium condition. So gas, CO2 gas is converted into what? Solution that you can say CO2 gas, right? So actually they were compressed into the liquid, and that's why we are seeing that whenever Coca-Cola or Pepsi or Mirinda or what any liquid or any cold drink that we are getting these days, when you will be opening the bottle of that, you will be finding that the gas is coming out from that liquid. Okay, now guys, see here. There are two types of reactions are there. One is what? Reversible reaction is there, right? Reversible reaction, and one is what? Irreversible reaction. A reversible and irreversible reaction, right? What is this irreversible reaction? See guys, reversible means what? It will come back, but the changes will be there. That will be back, right? An irreversible reaction, that will not be back, right? So a reaction in which not only the reactant reacts to form the product, but under the certain condition, also the product react to form reactants. Under the same condition is called reversible reaction. What I am trying to say, like a reactant is converted into product at the same condition. If the product is also converting into the reactant, then that type of reaction is called as what? Reversible reaction. Is it okay, guys? Getting my point? See here, 3Fe plus 4S2 is giving what? Fe3O4 plus 4S2. And at the same time, there is what? This forward and backward reaction is given here. It means what? This is changing into what? 3Fe plus 4S2. See here, CaCO3. This is what? Decomposition reaction that you are going to see here. CaCO3 is decomposing into what? CaO plus CO2, right? Now you are seeing that what? Backward reaction is also there. So CaO plus CO2 is converting into what? CaCO3. Is it okay? Sodium plus hydrogen, you can see here, Na plus 3S2 is converting into what? Ammonia, 2NH3. Now ammonia is also converting into what? 3S2 plus Na. Is it okay? So this is what? This is, we can say that the physical, or you can say the reversible reaction or reversible process is there. Is it okay, guys? Or reversible equilibrium is there. You can see that there is equilibrium is there. It means what? There, the science shows that is an equilibrium condition. Is it okay, guys? Is there any problem till here? No? No. No. If a reaction cannot take place in the reverse direction, that the product form do not react to give back the reactant under the same condition, it is called irreversible reaction. So you might have learnt in your earlier classes that what is this reversible reaction, what is this irreversible reaction. So the definition might be changed here, right? Although not completely changed, but the definition has been advanced here. Yes or no, guys? See here, what you are going to see here, if a reaction cannot take place in the reverse direction, right? That is, the product form do not react to give back reactants. If let's suppose whatever B has that has been formed, if it is not going to back, so then we will be calling this is what? Irreversible reaction. Is it okay here? So you can see here, you will be not seeing any back direction here, right? Only the forward reaction is there. No backward reactions will be there in case of irreversible reaction. Is it okay? So AgNO3 plus NaCl giving what? AgCl plus NaNO3. But it is not turning into back, and it is not giving again AgNO3 plus NaCl. Is it okay, guys? Now, 2Mg plus O2 giving what? 2MgO. But not 2MgO is converting into Mg plus O2. It is what? Irreversible reaction. Is it okay, guys? Now, one thing is that if any of the product will be removed from the system, so reversible reactions will become irreversible reaction. Getting my point, guys? So what is saying there? If any of the product will be removed from the system, then reversible reactions will become irreversible reaction. So whatever be the reversible reactions will be there, that will turn into what? Irreversible reaction if the product has been removed from the system. So please have a note of these things, then we will be moving ahead. Okay, guys. Now, see here. So the general reaction that we are going to see is what? How we are writing the general reaction is what? Let we have general reversible reaction. That is what? A plus B is giving what? C plus D. So it means what? C plus D is also converting into A plus B. If we are writing A plus B in forward direction, if we are writing what? C plus D, it means what? If this is a reversible reaction, so the backward reactions will be also there. So C and D will be also converting into A plus B. Is it okay? Now, so what is happening here? As the time passes, A and B will be converted into C and D, right? As soon as C and D will be formed, reaction will start in back direction also. A time will come when rate of decomposition of A plus B will be equal to the rate of formation, that is A plus B. So as we are seeing here, C plus D is what? Forming. After that, it will be what? That there will be decomposition will be there. So after the formation, there will be a decomposition will be there. So the reaction will be in backward direction. So we will be getting what? The rate of forward reactions will be equal to the rate of reverse reactions. At this stage, the reaction is said to be the stage of chemical equilibrium. Getting my point, everyone? So the rate of formation will be equal to the rate of decomposition. Now, come. See here. What is going to see here? That is what? Forward reactions and reverse reactions. See guys, what will be happening? At the equilibrium condition, at the equilibrium point, what will be happening? So they will be coming together and we will be getting what equilibrium point we will be going to get here. So one will be what? Forward. One will be what? Forward. And another will be what? Backward will be there, right? Another will be what? Backward will be there. And we'll be getting what? This type of reaction that we will be going to get. Is it okay? Please have a note of this, then we will be moving ahead. So is it okay, guys? So see here. When the equilibrium is reached, the concentration of reactant as well as the product remain constant. So here we will be going to see what? The reactant and product will be constant. Is it okay? At this stage, the reaction seems to be stopped, but in the actual, the reaction is going forward as well as reverse direction. See guys, actually at this stage, you will be seeing what? The reaction has been stopped, right? But the reaction has not been stopped here. What is happening here? The reaction is carrying out in the forward direction as well as in the backward direction. Is it okay? Is there any problem till here? So we are seeing what? The reaction, the direction of the same rate, and hence the equilibrium is called the dynamic equilibrium. So what we are going to see here, that is what? The dynamic equilibrium. The rate of forward reaction is equal to the rate of backward reaction. So that type of reaction will be called as what? Dynamic equilibrium. Is it okay, guys? Any problem till here? Okay, fine. Now see here. What are the characteristics of the chemical equilibrium that we are going to see here? What are the characteristics of chemical equilibrium? See here. The equilibrium is dynamic, that is reaction continues in both forward and reverse direction. If the reaction is continued in both forward and backward direction, then it is called as what? Then we can say that this is the characteristics of what? Chemical equilibrium, and it is called as what? Forward and backward reactions as well. Forward and backward reaction. This is the first point of the chemical equilibrium. Second point is what? The rate of forward reaction equal to the rate of reverse reaction. So whatever be the rate of, see guys, whatever be the rate of forward reactions and whatever be the rate of reverse reaction, they will be equal. And how we are finding the rate? How we are finding the rate, that we will be discussing in the later part of the class. Right? Let's suppose, just now I'm giving you a hint. Let's suppose we are having this reactant part, right? AA, BB, and giving what? CC, and DD. So rate will be what? Rate of reactant will be what? Do you know, guys? What will be the rate of this reaction? For rate of reaction, or we can say the forward reaction, it will be equals to what? Concentration of A to the power A into concentration of B to the power B. Yes or no? Oh, you might have not learned chemical kinetics. Okay, no problem. We'll be seeing in the next slide. The observable properties of the system such as pressure, concentration, density remains same, invariant with the time, or you can say same or invariant with the time, right? Next point. Once chemical equilibrium can be approached from the either side, right? So equilibrium can be approached from either side, or from the left side, or you can say from the right side as well. A catalyst can hasten the approach of equilibrium but does not alter the state of equilibrium. So catalyst is what? Catalyst can change the rate of reaction but cannot alter the equilibrium condition. Getting my point? We are knowing that we have seen so many reactions where the catalyst can increase the rate of reaction, right? You might be going to your doctor sometime, and doctor is saying what? Like you can have enzymes in your food. Like if they're, let's suppose if your mom or dad is complaining that my daughter or my child is not eating, or they are not having the proper diet, so the doctor is giving you what? Doctor is giving you enzyme, right? Enzyme. And what is the work of that enzyme? Enzyme doesn't do anything, right? Just increase the rate of your, digestion. So if the rate of digestion will be increased, so what will happen? Automatically you will be having what? You will be starving, that you want some food after that, right? So the rate of reactions has been increased, like whatever be the rate earlier was there for the process of digestion. So that has been increased only. So you will be in search of food after that. So that is happening with the case of catalyst, right? But it will not alter the condition of the what? The equilibrium. Is it okay? Fine. Now see here. There are mainly two types of equilibria. Homogeneous. Equilibrium is said to be homogeneous if the reactant and product are in same phase, right? Same phase. So this is what? Homogeneous. So let's suppose H2, that is what? Gas. I2, that is what? Gas. We are getting what? 2HI, that is what? Gas. So gas. We are getting what? Gas only. So their phase is what? Phase has not been changed. Either from solid to liquid, liquid to solid, liquid to gas, liquid to solid. This has not been changed. It is what? Only the gas is converted into gas only. H2 gas plus I2 gas is converting into what? HI gas. And again HI gas is converting into what? I2 plus H2 gas only. So this is what? Phase is not changing. So if phase is not changing, then this type of equilibrium will be called as what? Homogeneous equilibrium. Is it okay, guys? Any problem? No? See here. Another example is what? N2 gas plus 3H2 gas. We are getting what we are going to get here? 2NH3. NH3 is what? Ammonia. Ammonia is what? Gas only. So this is what? The phase has not been changed here again. Any problem? No? No. Next example is what? N2O4. That is what? Gas. Again we are getting what? 2NO2. That is what? Gas only. Okay. CH3COH. This is what? Liquid. That is what? Carboxylic acid. CH3COH. CH3COOH. Ethanoic acid is there, right? Ethanoic acid and C2H5OH. This is what? Alcohol. Guys, this is what? Nothing. This is alcohol only. Ethanol. So this is also liquid. This is also liquid. And again we are going to get what? CH3COO C2H5, right? and H2O. This is what, this both are what, liquid only. So liquid, 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 everything is liquid. So phase is not changing there. So it will be called as what? This is the type of homogeneous equilibrium. Is it okay? Any doubt? Okay, let me ask some questions from others, guys. So Asrita Nahak, what is this homogeneous equilibrium?
If reactant and product are in same phase, then it's called homogeneous equilibrium.
Okay, that's great. So if I am mixing with acid with alcohol, and again if you are getting what, acid and water, or alcohol or water, or acetate or water, and they are in liquid condition only, so will they will be in the same phase, or they will be called homogeneous mix?
Same phase because they are in liquid.
So they will be called as homogeneous equilibrium, right?
Yes, sir.
Okay, fine. Now we are going to discuss about what heterogeneous equilibrium, right? What is this heterogeneous equilibrium? So I hope now you are having some idea about the heterogeneous equilibrium, right? Because earlier we have seen what, the same phase, so it will be called as what, homo. So if people coming from the biology side, they are knowing that what is this homo, because there's also they are learning about this homo, right? Homo means what? Same. Hetero means what? Different. Okay. Homo means what? Same. That is, we have seen same phase. And hetero means what? Different phase. Different phase means what? Either solid, liquid, solid gas, solid liquid. Anything can be there, right? No solid, no liquid, no gas will be there. Is it okay, guys? Now you are saying here that what? Equilibrium is said to be heterogeneous if reactant and product are in different phases of solid. Like CaCO3 is a solid, and again, if it is converted, it is converted into what? CaO plus CO2. CO2 is a gas that you are knowing. CO2 what? CO2 is what? Nothing. This is carbon dioxide. This is what? Gas only, guys. So in three things, that is one in reactant and product, solid and solid, but the CO2 gas that is evolving here, that is what? Gas. So we cannot say this is a homogeneous equilibrium. This is what? Heterogeneous equilibrium. Is it okay? Again here you can see NH4HS plus giving what? NH3. Although they are in what? Equilibrium condition, but which kind of equilibrium is here? They are in what? They are not a homogeneous equilibrium. They are in heterogeneous equilibrium. Is it okay, guys? Any problem till here? NH2CO, NH4. NH2CO2, NH4 is giving what? 2NH3. That is what? Gas again. And CO2 is what? Gas. So solid is converting into gas and gas only. So this will be what? This will be a type of heterogeneous equilibrium. Is it okay? Now, to write the equilibrium constant expression, that we will be going to see in the next part, right? How to write the equilibrium constant. If you want to have a note of this, guys, please have a note of this, then we will be moving ahead. Okay, guys, see here now. Now we are going to see about what law of mass action. Do you want break? Yes or no, guys? Please say me. No one is saying anything. Aniska, Atacha, Raghav, Vana, what do you say? Do you want break? Yes? Okay. So take a break of 5 to 10 minutes, then we will be back, then we will again start. Hello everyone, please turn on your camera. Okay, so are you able to see your class assessment and homework? Please guys, please check first. Yes? Are you able to see your class assessment and homework? Okay, fine. So now we are going to see about the law of mass action, right? What is this law of mass action that we are going to see? See guys, actually we are having what? The concentration A, B, B, right? And it is forming what? C, C, and D, D, right? Let's suppose if we have to find the rate of forward reaction, right? Although here only the rate of forward reaction is happening, not the rate of backward that we are going to see here. So rate of reactions will be what? We can write like this. The rate of reactions, we can write like this. Rate of reaction is directly proportional to what? Concentration of A to the power what? A, and concentration of B to the power B. If we are removing this corresponding sign, then we have to bring some constant there, right? So we'll be writing what? Rate of reaction. Rate of reaction equals to what? K into concentration of A to the power A into concentration of B to the power B. Is it okay? K is nothing here. K is what? Rate constant or velocity constant. Is it okay, guys? But if let's suppose if I'm saying what? Rate of backward reactions. Let's suppose here we have written what? Rate about the rate of forward reactions. We can say what? K we can take here what? K is what? Nothing. This is K is what? Kf we can take. And Kf is what? Rate of forward reactions. So first of all, see here what is this law of mass action is saying here. Bulberg and Weiss established the relationship between the rate of chemical reaction and concentration of reactant or their partial pressure in the form of law of mass action. According to this law, the rate at which the substance reacts is directly proportional to the active mass and rate of chemical reaction is directly proportional. Who has opened their mic? Guys, try to see here. Yes. So we have seen what? Rate is directly proportional to what? The concentration terms, right? What are the concentration terms here? That we are having what? A to the power A. That is what? A to the power A means what? The concentration of A to the power. This is what? Coefficient here. To the power coefficient. Coefficient is what? A. That will be written here. Is it okay? Same we have written here also. Concentration of A to the power A and concentration of B to the power B. If we have to move the reaction in the backward direction, then what I will be writing here in this is C to the power C and into concentration of D to the power D. Is it okay? Now, the rate at which the substance reacts is directly proportional to the active mass and the rate of chemical reaction is directly proportional to the product of active mass of the reactant, each raised to the power equal to the corresponding stoichiometry. Getting my point, everyone? And appearing in a balanced chemical equation that we are seeing here. Guys, what is this law of mass action? Yes, Kanishka, you can. Guys, who has understood this law of mass action, please tell me. What is this law of mass action? What is this law of mass action? Who will tell me? Raghav, have you understood this? Raghav, what is this law of mass action? Have you understood this? Asrita Nahak, what is this law of mass action?
Sir, law of mass action, law stating that the rate of any chemical reaction is proportional to the product of the masses of reacting substance.
Yes,
With
that is good. With their coefficient.
each mass,
Yes.
yes, sir. With
Each
each
mass will be.
mass raised to a power equal to the coefficient that occurs in the chemical equation.
Yes, that you can see here. Here is what? If I will have to write rate of forward reaction, then what I will be writing here? Rate is directly proportional to what? Concentration of A to the power A. What is this? This is saying that law of mass act, that concentration of A to the raised to the power A. That is what? Stoichiometric coefficient. A is nothing here. A is what? Stoichiometric coefficient, right? You can see here. A is what? Stoichiometric coefficient of A. B, small b is what? Rate of this is what? Stoichiometric coefficient of B. So that we will be writing here. B to the power B. Is it okay? So for this removing, if we have to remove this prosperity sign, we have to do what? We have to take one constant, and that constant is what? That is nothing. That is what? K. And if the reaction is forward in the forward direction, we can take it as a Kf. If the reaction will be in the backward direction, then we will be taking what? Rb. Is it okay, guys? So concentration of A to the power A into concentration of B to the power B. Is it okay here? So that is saying here what? Law of mass action is saying what? The rate at which the substance reacts is directly proportional to its active mass, and rate of chemical reaction is directly proportional to the product of active mass. Product of active mass of reactant each raised to power equal to the corresponding stoichiometric coefficient appearing in balanced chemical equation. Is it okay? Is it okay, guys? Now see here. So this is for what? Forward reaction. If we have to write for the writing for backward reactions, so rate will be equals to what? Rate will be equals to what? Kf proposed Kf into what? Coefficient of the C to the power C into D to the power what? D. This will be in the backward reaction. See guys, this will be in backward Kb. I will be writing what? Kb. Rate equals to Kb into C to the power C into D to the power D. And in forward, if you have to write, that will be equals to what? R equals to Kf into A to the power A into a concentration of B to the power B. Is it okay? Now see here. Unit of rate constant K is what? Mole per liter into C here. Where N is what? In order of reaction. That we will be seeing later, right? Now. See here. Here we are having what? Equilibrium condition. In the equilibrium condition, rate of reaction, that is forward and backward, will be equal. Yes or no, guys? But we have seen that rate of forward reactions is equal to the rate of backward reaction. So now see here. For unit concentration of reactant, rate of reaction is equal to the rate of constant or specific reactions rate. So at equilibrium, the rate both forward and backward reactions become equal, and after achieving the equilibrium, the concentration of the reactant and product remains constant as shown. We will be also seeing the relation between what? This relation between Kf and Kb. We are going to see what? Kf. What will be the relation between Kf and Kb? Kf is what? Rate of, that is what? Forward, and Kb is what? Backward. See here. Alpha A or A, small a, you can say A, B, B is there, right? So if we have to write according to the law of mass action, rate of forward reaction, if I have to write what? Rate of forward reaction. Rate of forward reaction, if I have to write, then what I will be writing? Rate of forward reaction equals to what? Who is there? Yes, Atachaya will be helping me. What will be the rate of forward reactions? Can you please tell me, Atachaya? Seeing this equation, can you please tell me what will be the rate of forward reaction? See this equation and tell me what will be the rate of forward reaction.
The A concentrate of
A, concentration of A to the power
A
and into
B concentrate
concentration of B to the power B. That we will be writing like this, right?
Yes.
And see, actually these are in directly proportional, right? See here. Actually what happens? Rate is directly proportional to concentration of A to the power A into B to the power B, right? So to remove this sign, we have to bring what? Constant any. So with that constant that I am taking what? Kb. Kb into A to the power A into B to the power B, right? This will be the right equation for forward reaction. Yes or no? Atacha, am I right here? For forward reactions, can we write like this?
Yes, sir. Yes, sir.
Yes, no. If I have to write for the backward reaction, so what I will be writing for the backward reaction then? Because the reaction is same, right? The reaction is what? This is the reaction. AABBCCDD, right? So if I have to write for the backward reaction, so what I will be writing for the rate of reaction, rate of backward reaction, that what I will be going to write for this. So here I will be writing what? KB into A to the power A into B to the power B, right? So backward reactions, so see KF, actually it is forward. So KF I will be writing here. So can I write here KB into concentration of C to the power C into concentration of D to the power D. Can I write like this? Yes or no? Please say me. Guys, what do you say? Atachaya, what do you say? Can I write like this rate of backward reaction, that is Kb into concentration of C to the power C into concentration of D to the power D? Yes. Now, see. Actually, we have to do what? We have to do what? If, can we write like this now? See here. If we are equating this two term, Kb into concentration of A to the power A into concentration of B to the power B, right? Equals to, sorry, here Kf was there, Kf, Kb into concentration of C to the power C into concentration of D to the power D. If I will bring this Kb to this side, so what will be happening there? So left hand side will go to the right hand side then? Yes or no, guys? What do you say? So Kf upon Kb equals to what? Concentration of C to the power C into concentration of D to the power D upon concentration of A to the power A into concentration of B to the power B. What do you say, guys? So Kf upon Kb equals to concentration of C to the power C into concentration of D to the power D upon concentration of A to the power A into concentration of B to the power B. Is it okay? Please have a note of all these things, guys, then we will be moving ahead. So guys, so what we have done here, I hope everybody has written these things. So rate of forward reaction equals to the rate of reverse reaction. So that's why I have written what? Rate of forward reaction equals to the rate of backward reaction. So what we have found here after this, Kf upon Kb equals to what? Concentration of C to the power C into concentration of D to the power D upon concentration of A to the power A into concentration of B to the power B. That we have got here. Okay, everyone. In some books, instead of Kf, they are writing what? K1 and K2. So don't worry about this. What is this K1 and K2? I hope everybody has understood this K1 and K2. Who has not got this, please tell me, guys. K1 and K2 or R1 and R2, rate 1, rate 2. That I have taken here what? That I am taking only R here. Rate of forward reactions, I can take R1. Rate of backward reaction, I can take R2. For this Kf, I can take what? K1. For this Kb, I can take what? K2. It's totally up to me and totally up to you only that what you are going to take and what I am taking here. Is it okay, guys? Is there any problem till here? No? See guys, this A is what? This is nothing. Molar concentration of A. That's in the bracket that we have written what? In the big bracket or square bracket that we have written A. This is what? Molar concentration or concentration. I was using the term again and again, that is concentration. This is nothing. This is what? Concentration or molar concentration. The molar concentration is that the number of moles per liter is called the active mass only. The molar concentration is that number of moles per liter is called what? Active mass. It is expressed by including the symbol formula of the substance in square bracket. That is what? A. Square bracket. Is it okay, guys? Guys, please go through once again. What is this law of mass action? Relationship is known as what? Relation between what? Concentration of A into concentration of B and what? Concentration of C and concentration of D, and that is what? Proportionality constant. See here. It states that the rate of a chemical reaction is directly proportional to the product of the molar concentration of the reactant at a constant temperature at a given time. This is mass of action. Law of mass action. Okay, now. This we have seen, guys, earlier. This also we have seen, rate of reaction, rate of backward reaction, that we have seen. Okay, everyone. Now. See, this is one question that we are having what? 2A plus 3B. 2A plus 3B. If we have to write rate, so how I will be going to write the rate? Guys, how I will be going to write the rate? According to the law of mass action, how I will be writing the rate of reaction? See, can we write like this? See here. See, rate at which A reacts. For that, what I will be going to write? Concentration of A into C. That is 2A is there. So can we write e to the power 2? Because coefficient is what? 2 is there. So we will be writing just 2 only. And for this B, what I will be going to write for this? Concentration of B to the power what? 3. Is it okay? The rate constant of a reaction at given temperature may be defined as the rate of reaction when concentration of each reactant is unity. That is, that we can write like this. Now, see here. Let's suppose in case of not A and B, if there will be three terms will be there, or you can say three molar mass will be there, then what I will be going to write for that? See here, AA plus BB plus CC will be there, and product something will be there, right? So for that, rate of reaction R will be equals to what? Constant K into coefficient C, concentration of A to the power A into concentration of B to the power B into concentration of C to the power C. Is it okay, guys? Is there any problem till here? See, guys, for the previous one, if I have to write the rate, then what I will be going to write here? Rate concentration of A to the power 2 into concentration of B to the power what? 3. And there must be something constant will be there. Okay. So can we write like this? What? K into A to the power 2 into B to the power 3. And for here, if I have to write the rate, so what I will be going to write? Concentration of A to the power A into concentration of B to the power B into concentration of C to the power C, and K will be multiplied by this. Okay, everyone. Law of mass action we have seen. Now, this also we have seen, guys. Here there will be what? B will be there, right? Kf, that is into concentration of A into concentration of A into concentration of B equals to Kb into concentration of C into concentration of D. And Kf upon Kb will be equals to what? This will be going down and this will be remain same here. So concentration of C to the power C into concentration of D upon concentration of A upon concentration of B will be there. So if I have to find what? K, value of K, if we have to find K, then we can do like this. So who has got that? How we can find the value of K? Kaniska and Natachaya, can you please tell me how we can find the value of K? If we have to find the value of K, so how we can find the value of K? See, first of all, we will be seeing rate. Rate equals to what? K into K. That is what? That this can be forward, that we can write Kf, right? So this will be if the reaction is what? AA plus BB gives what? CC plus DD, right? If this is the reaction, then rate equals to what? Kf into concentration of A to the power A into concentration of B to the power B. Guys, please try to understand here, because I am telling these things again and again. This is important one, and this will come in your numerical part as well. Now, this is what? R1, let's suppose this is forward reaction for the rate for the forward reaction. Rate for the backward reaction, if I have to write, that is R2, let's suppose I am taking. So Kb equals to what? Equals to Kb into concentration of C to the power C into concentration of D to the power D. If I will be going to equal these things, right? Because what? Rate of forward reaction equals to rate of backward reaction. Yes or no, guys? Please try to concentrate here. Atachaya, Kaniska, Bhuwana, Raghav, Sridhar, Nahak, Mukeshwan, everyone. Rate of forward reaction equals to rate of backward reaction. So I am going to equalize these two things. So I will be writing what? R1 equals to R2, right? If I will be going to write R1 equals to R2, so I will be writing what? Kb equals to Kb into, see guys, so if that, then what I can write here? Kb, if I have to find what? K or Kb or K, anything if we have to find. So Kb, Kf upon Kb will be equals to what? See guys, Kf upon Kb equals to what? This will be going, see, actually they will be going down. See here, from this reaction also we can see Kf into concentration of A into concentration of B. So if we have to find Kf upon Kb, so I will be bringing this down, Kf upon Kb, and this A and B part will be going down of C and D. So so we will be getting what? K equals to concentration of C into concentration of D upon concentration of A upon concentration of B. Is it okay, everyone? Now, concentration quotient, that is what? Q. This is nothing that we have got what? Concentration of C into concentration of D upon concentration of A into concentration of B. So Kf upon Kb equals to what? Is called equilibrium. And constant has a constant value of a reaction at a given temperature. The concentration ratio, that is ratio of the product of concentration of the product of the reactant, is also known as concentration quotient. That is denoted by what? Q. So that is nothing. Concentration of C into concentration of D upon concentration of A into concentration of B equals to what? That is Q. This is nothing. This is Q only.